3 y 2.
Ah, es verdad que se va.
No, no lo sabía. Son las 3 y 2. Yo va exacto, y 2 y 30 segundos.
Esperamos en 3 y empezamos. Welcome everybody. All of you should now know João Bettencourt. You know that he's doing the PhD here on some problems on fluid dynamics. Probably most of you don't know that before coming here, João did a master on naval engineering in Lisbon University, Lisbon Technical University, and the master thesis title was something like "Performance of a Sail."
Yeah.
So, and after this, he went to Norway to work on a company for designing propellers, blades of propellers. So he knows a lot about the forces of water and air on objects, on ships, on airplanes. So this is what he will talk about.
Hello everyone. Since this is an interdisciplinary institute, I took the liberty of bringing an off-topic to the seminar and something a little bit different that you really see, but I hope you find it interesting. First, I'll talk about design methods in incompressible aerodynamics. Of course, aerodynamics is a very wide research topic, and these design methods, they are basically what people do is that they gather all these research results and they try to make something workable out of it, I mean, in the design environment. So, of course, there are 100 years or more of research that it's kind of impossible to squeeze in 40 minutes. So I'll just talk about the basics, especially these potential flow methods that are quite old and quite simple, but they are very useful. They prove to be very useful. And lately, now this is I'll talk about computational fluid dynamics. That is now a hot topic in aerodynamic design. And I will talk about this. I'll talk especially about turbulence modeling because it's like the Achilles heel of this computational fluid dynamics. And then I'll finish with an example. Of course, the problem in aerodynamic design, and I'm a professor, I'm a naval engineer, so I work mostly with propellers and ships, but I chose the aerodynamics because the equations and the methods are the same, and it turns out there's a lot more material on wings and such devices than on nautical applications. So the problem with the aerodynamic design is that we want to find the forces that are acting on this wing. Here is the cross section. We want to find the forces that are acting on this wing when it's subject to an airstream with the velocity v and at an incidence angle that we call the angle of attack. It's called alpha. And actually the resultant force is this vector r here. But in aerodynamic, it's usual that we decompose this r vector into two components. One of them is parallel to the velocity stream, and it's called the drag, it's d. And the other one is it's called the lift, and it's normal to the velocity stream. So of course the lift in an airplane is what keeps it flying up there. And of course the drag is what we pay for if we want to fly it. So if we use dynamical analysis on this problem, we'll find these very simple expressions that relate these two forces to the parameters of the flow and also to the shape of the wing. And we get that these forces, they are directly proportional to the density of the flow of the fluid, to the square of the free stream velocity, and to the area of the wing, both for the lift and the drag. But we also have that they are directly proportional to these two coefficients that, as it turns out, they're the tricky part of these equations. Before I go on to discuss this, I just wanted to give a little historical note. You can see we can start, as always, by Leonardo da Vinci, and then we can go all the way up to the 16th century, and we see that scientists were already more or less in agreement about these three terms here. Of course, a lot has been done since, but up to date it's still difficult. It's still tricky to calculate these two coefficients directly. Now I want to try to show you why. Of course, these two coefficients, they depend on the pressure and the shear stress distribution over the wing surface. Now, the lift coefficient and the lift force, we know that it depends more or less solely on the pressure distribution. And you can see here the physical mechanism of lift that is due to this pressure difference between the low part, underneath the wing where you have a high pressure, and above the wing when we have a low pressure. This is called the pressure phase, and this part here, the top of the wing, is called the suction phase, and this pressure differential creates the lift on the wing. Of course, we also have this shear stress distribution that is like the stress of the friction of the fluid over the surface, and that is mostly depends on what's happening in the boundary layer, which is this very thin region here on the surface of the wing where viscous effects are important. So what happens here more or less determines this shear stress distribution. Now, just to ease up things a little bit, if we do the dimensional analysis, the same that we did before for the forces, we'll find that these two coefficients, they are functions of the angle of incidence, the angle of attack, and the Reynolds number. This Reynolds number is mostly related to this part, while the angle of the attack is related to both. Now, before we start, I'd just like to talk about nomenclature. Of course, a wing is defined in terms of its platform, that is more or less what we see when we look at it from above, and by the shape of its sections that we call the airfoils. Now, the platform, we can define its span, which is constant for a platform, and also the chord, which is its shortest dimension. Of course, this chord value may vary along the span. There is another important parameter about this platform of the wing, which is the aspect ratio, and it's just a measure of how elongated the wing is. And it turns out, as I'll show you later, that it is very important in aerodynamics. And now about the airfoils, they're defined mostly by their thickness distribution. It is just the distribution of the thickness around this chord line, and also by the camber, which is just a measure of the curvature of the airfoil. Higher camber means higher curvature. Now, of course, this is just the common, simplest wing platform, but there are other platforms, like I show you here, just as an example of how widely varying these platforms can be. Here we have the delta wing of the famous Concorde, and over here we have a kind of wing that is called the forward swept wing, because the platform is swept forward. Actually, these two types are more used in supersonic flight, so I won't be discussing them here. And of course, about airfoils, you can see here this is just a kind of a historical evolution of airfoils, but you can see that it started more or less like these very thin sheets, almost lines, highly curved. Then they progressed through the years until they become all these more thick, almost symmetrical airfoils. So there's a lot of variation, and inclusively I can say that there are thousands of different of these profiles. Okay, now just a short note about how these force coefficients, they vary in an airfoil. I told you there were functions of the Reynolds number and the angle of attack. And now for the lift coefficient, which is mostly this curve here, you can see that it's approximately linear with respect to the angle of attack, and until it reaches this maximum here, this is called the maximum lift coefficient, more or less between 10-20 degrees usually, and then it falls off sharply. Now when it falls off, that's when we say that the wing is stalling, because it cannot produce lift. Now, as you can see here, there are three curves. It's a little bit difficult to see. There are three curves, but for low angles of attack, the curves just collapse on each other. And you can see that the variation due to the Reynolds numbers, these are different Reynolds numbers, it's just over here near the maximum lift coefficient. Of course, for a symmetric airfoil, since the pressure distribution when the incidence is zero is symmetric, the lift is zero. But if we had a cambered airfoil with curvature, then at zero incidence the lift would have a positive value, because the pressure distribution wouldn't be symmetric then. About the drag coefficient for a symmetric airfoil, you can see it has a minimum here at zero incident, and it just grows steadily over the range of angles of attack. And you can also see that there is a little variation here with the Reynolds number when we have near the angle of maximum lift, which is more or less this one. Of course, for a symmetric airfoil, for a cambered airfoil, an airfoil with a curve, this minimum wouldn't be here, wouldn't be around here in this low region of angles of attack. Okay, that's about what to say. So now, before I go into 3 dimensions, I'd like to show you how can we calculate the lift and the drag of an airfoil, which is a study in 2 dimensions. Now, I'm going to use a potential flow method in which we disregard viscosity. So we have a flow in a viscid fluid and also a stationary flow, just to make things simpler. Now we have here our airfoil, and I'm going to surround it with this control volume that's made up of these 2 parallel surfaces, which I say are streamlines of the flow, so that the velocity vector is parallel, and also this upstream and this downstream boundaries here. The velocity at the upstream boundaries is u1, and the velocity at the downstream boundary is u2. And now I'm going to apply some conservation principles to just try to find out the forces. Of course, mass conservation, since this is a streamline and the velocity is tangent to this line, there is no fluid crossing these 2 surfaces. So what goes in through here, and what goes out through here. And so since these 2 dimensions are equal, for we have the same mass going in and going out, we must have that these 2 normal components, this u1n and u2n, they must be the same, so that mass is conserved inside this control volume. Now, about the momentum conservation, where we would like to find the forces, we should note that, of course, this is a streamline, they are parallel, so there is also no transport of momentum through them. But beyond that, the normals of these 2 lines, they have the same direction but have opposite senses, so that, for instance, when we go and integrate the pressure term here and here, they will cancel out. Now, if I make this momentum conservation on the x direction, I get that momentum transport cancels, because these 2 velocities are the same, and all I have left is this difference in the pressure force here and here, and that gives me the force in the horizontal direction. Now for the vertical part, since I don't have any pressure terms acting here because they cancel out, I'm only left with this expression, and this expression is just the force that is generated when the flow turns to pass around the airfoil and leaves here. And now, if I'm going too fast, just ask me if you have any question, please. Now that we have these 2 expressions for the lift and drag, for the forces on the airfoil, I would just like to get rid of these pressure terms here, and I'm going to do that by using Bernoulli's law, which is just the way that the conservation of energy along a streamline. Now I can use this to replace these pressure terms with velocity terms And now I'm going to define this mean velocity components, which is the mean of the normal components and of the tangential components. And with this I get these two expressions for the forces that they are just in terms of the velocity here. Okay, and now I'm going to introduce a very important quantity in aerodynamics. It's called the velocity circulation. And the velocity circulation is just the integral of the velocity vector along a closed contour, encircling, for instance, the airfoil. Now, if we apply this integral to this configuration, we get this expression, and I can use it to replace these expressions here, and I get this quite useful result, as you will see next, that the horizontal and the vertical forces, they're just the density times the mean velocities and the velocity circulation. Okay, now we're getting close to where we wanted. So now I'm going to introduce a very important theorem in aerodynamics that is called the Kutta-Joukowski theorem. Because we now have these forces, a vertical and an horizontal and a vertical one, but in the beginning I defined aerodynamic forces in terms of their orientation with respect to a mean velocity that I'm drawing here. So now what I'm going to do is I'm going to express these forces into this axis system, which is parallel and normal to the velocity vector, this mean velocity. Now when I do that, I get this very surprising result that the parallel component is 0, which means that the drag of this airfoil does not exist, it's 0, and that the lift force is equal to the product of the density, the mean velocity here, and the velocity circulation around the airfoil. Now, of course, to start with this quite unusual result, because one would expect that the body in a flow would offer some resistance. This result was first discovered by D'Alembert in 1752, and it has been since been known as D'Alembert Paradox. Of course, at that time the effects of viscosity in fluid flows weren't really well understood, so they got a little bit surprised and they called it a paradox. But now, of course, we know that this result is 0 because viscosity is discarded in potential flow calculations. And actually, with real fluids that have viscosity, the drag it's not 0 at all. So just now, just to finish this part, note that with this expression here and with the expression, the first expressions of the lift force, I can finally find a value for that lift coefficient. Of course, the drag coefficient in potential flow is 0. Okay, now moving on to the wings, to three dimensions. I'm going to introduce this. It's very old, and it's a very elegant theory that Prandtl developed to explain the lift and drag of three-dimensional wings. And the idea is that if in 2 dimensions the lift force of an airfoil is related to the circulation around it, then perhaps in 3 dimensions the lift of a wing is related to the circulation around its sections, which are airfoils. So that means that if we can get a distribution of circulation along this span, every section, every airfoil of this wing will have a circulation around it, and it will be producing lift. Now we can do that if I introduce here this bound vortex. It's just a vortex line that extending throughout the span of the wing, and it says along its length it has circulation around it, so that every section of the wing is having a circulation around it. Of course, this I can do. I just can't do this like this, because there are some theorems, Helmholtz theorems, about circulation and vortex lines in potential flows that they say, among other things, that first, these vortex lines, they cannot start and end in the fluid. They either must extend to infinity or end at the solid wall. So what I'm going to do is I'm going to make this vortex line extend to infinity by adding these two vortex segments that they leave the vortex line and they extend up to infinity. So that actually what we have here is an infinite length, a vortex line of infinite length starting at minus infinity, going around and finishing off at minus infinity too. This construction is called a horseshoe vortex. It's very useful in potential flow theory, but it has a problem. It's because the second of Helmholtz theorems says that the circulation distribution along this vortex line must be constant. And that is quite not what we expect, because if we think about reality and a three-dimensional wing, we really don't expect it to have a lift distribution that is constant along its span. Especially here at the tips, where the pressure, the high pressure from the pressure phase equalizes with the low pressure from the suction phase, we should have zero lift, because there is no pressure difference. So, but it turns out that we can actually model a varying lift distribution along this vortex line, but just that we have at each place where the velocity, where the circulation changes value, we have to take that change all the way down to infinity. So what Prandtl did was he introduced this set of trailing vortices that extend continually along the span of the wing, and they extend to infinity. And if you note that the strength of each of these trailing vortices is related to the change in circulation along this wing, so that actually the whole circulation is zero. Change in circulation is zero when we account for these trailing vortices. Of course, we're not finished yet with Helmholtz theorems, because there is a third, and it says that fluid flows that start irrotational, I mean with no rotation, they must remain in rotation. So now that we are introducing rotationality in our fluid flow, we must take it out, and we do that by adding a starting vortex right downstream at infinity, so that it will cancel this bound vortex over here. Okay, and now we have a vortex system that really is in agreement with the theorem, so we are much more safe now. Of course, there are no free lunches, so now we have to see what are the effects of having these trailing vortices and the starting vortex here on this vortex line, which it's called a bound vortex, because it's bound to the wing and it's simulating the wing generating lift. Now, the starting vortex, it's downstream at infinity, so we really don't need to concern ourselves with them, because we can neglect its effect. But we have to take into account these trailing vortices here. Now, if you note that the orientation of these vortices is such that here on the lifting line, their effect is to create a vertical velocity down at every point here on the bound vortex. So we have to look at it and see what happens because of this induced vertical velocity. So it might seem a bit confused, but of course here we have the original free stream velocity here on our wing section, but now we have this induced vertical velocity from the trailing vortices. And what this does is, this was the original incidence angle, the angle of attack, but what this induced velocity does, it will change the direction of the free stream velocity up to this effective velocity here. And now we have a new incidence angle, that is the effective angle of attack. And when we think about two dimensions where we didn't have any drag, just a lift force, we see that this blue lift force is the lift force associated with this velocity here. Now, because this effective angle is smaller than this original angle of attack, we know, if you remember that slide on the CL and CD, we know that this lift will be lower, because lower angle of attack gives a lower lift coefficient. So this is a quite interesting result, is that due to this three-dimensional vortex system, an airfoil that is working in 3 dimensions has less lift at the same angle of attack than it would have if it was working in 2 dimensions. The second effect is that we can see now that this effective lift, when we look at the original free stream velocity, it's inclined to it. And so we do have this normal component, which is our lift. But now we also have this parallel component, which is a drag. And that's also quite surprising because I have just shown you that airfoil sections do not have any drag. Of course, this drag is induced by this velocity, and so it's called the induced drag. And you can see that it's simply related to this 2-dimensional lift by this induced angle of attack. Now we know more or less what's happening. So now the idea is that if I define here the circulation distribution and take into account all of this, I can find the total lift and drag of a wing. So now what I do is I just put here a general circulation distribution. I won't discuss this formula a lot, but it comes from this theta, comes from a change of variables with this z variable here. And now, if I want to find the lift of the total wing, I'll just use the Kutta-Joukowski formula that I showed you back there, and I'll just sum the lift of every wing section, as I do here, and then I get this lift coefficient formula. And you can see that here is the aspect ratio that I talked to you about. And I can do the same for the induced drag coefficient. But now looking at this formula, and I see that I have to know the value of this induced angle of attack. It comes from the induced velocity. So now, at each point in this lifting line, I'm going to calculate the induced velocity by a single trailing vortex. This is just the Biot-Savart's law. And to find the total induced velocity here, I just have to integrate all along theta or z. So now I have the total induced velocity. And now I can really use this velocity here to find the induced drag at each section. And again, I'll just integrate it, and there is some mathematical things going on here, so that we finally integrating along this line, we have this induced drag coefficient. That's what we are looking for. Of course, a real wing in real flow has viscous drag, but since it's potential flow, we neglect this viscous effect. Okay, so now that I have this aerodynamic force coefficients, I'm going to show that there is a very, very close relationship between.
What was B? Sorry, what was B? Capital B?
Sorry. B, this B1, Bn, they're just the coefficients of this of the circulation
profile you choose.
Circulation profile.
So that depends on that will be on the design of the.
Yeah, that would be on the design. Actually, there is
on the section of the wing or something like that.
Yeah, it depends. Actually, there is a method. Actually, if you equate some of these equations, you can get a linear system that when you solve, you get all of these coefficients. But I decided not to show it because it's really just algebra. So now that we have these lift coefficients and this induced drag, I can show that there is this quite clear relation between them. You can see that the induced drag coefficient is proportional to the square of the lift coefficient over the aspect ratio, and here with this small b parameter that I'll talk just a little bit later. Now, what I wanted to tell you is that with this relation you can see that this induced drag, it exists because we have lift, so that you can see it's like the price we pay for for a wing generating lift. And physically, I can show you this very nice picture. What happens is that if you think that before this airplane passed to this region, and if there was no wind, all this fluid will be at rest. But now that he has passed, all this fluid is in motion. And of course, to set fluid in motion, you have to impart energy to the fluid. And actually what happens is that this induced drag is just a measure of the energy that the wing is imparting to the fluid just to make it rotate. And now to discuss about this small e parameter.
João, the expression you have obtained for CL, for the lift, is valid for any arbitrary shape of the airfoil?
No.
Which are the assumptions that you made for the airfoil?
Oh, for an airfoil, yeah, it's valid for any shape of an airfoil, but not for every shape of a wing.
Okay, that's the shape of wing.
Yeah, because
so it's a.
You see, you can have whatever shape you want to.
Okay, but the wing must be rectangular.
It must be rectangular and must be flat.
Where does the information of the airfoil goes into the coefficients here? Because the different airfoils might have different lift or not.
Yeah, of course.
So where does that go in this approximation?
Different airfoils give different lift, and that when you solve this system of equations that I told you about, you'll get, and this lift of an airfoil will be reflected here on
Going to be as well.
on these coefficients.
To understand the difference between 2 and 3 dimensions, I understand that the main difference. So in a wing in which the wing goes is infinite in width, you should recover the 2-dimensional result. Is this right?
Of course.
So is it because you have borders in the wing that the lift becomes reduced, and you have this extra
resistance? Yes, that's correct. That's exactly it. So here, this small e here is called the Oswald efficiency factor. You see that the most efficient wing would have this value equal to 1 from this formula. And actually you can demonstrate that this happens when the distribution of circulation is elliptic, has an elliptic shape. And I can show you here, this is the Spitfire. And it was designed exactly to have this elliptic distribution of circulation. In the end, due to the assumptions they use, they end up with this kind of elliptic wings also. Okay. But so
that's to minimize the Oswald factor.
Yeah. Actually, it happens
to minimize the drag.
Yeah, it will minimize this induced drag. I mean, when it's 1, this factor cannot be greater than 1.
Yeah.
So when it's 1, we minimize. And it happens when we have an elliptic distribution of tau. It doesn't mean that the wings have to be elliptic. They can have other shape, but it depends on what you assemble. Now, okay. So I was saying this lifting line theory is very useful, but it's very limited because you need to have rectangular wings. They have to be flat, and they cannot have. So they leave out a lot of useful wing shapes that are used today. So I'm going to show you here another method. It's called the Vortex lattice method. It's come from 1946, and it works like this. We discretize. This is the wing surface, the mean wing surface, the planform, and we discretize it. We divide it in these rectangular panels, and on each panel we put a horseshoe vortex with constant circulation, and we define also these points that we call the control points. Of course, this system, all of these horseshoe vortices, they will induce again vertical velocities, but we know since the wing surface is a solid, it's impermeable. I mean the velocity vector there cannot be velocity crossing this wing surface. So we can find a mathematical condition for this, that, for instance, in this control point I, we sum all of the induced velocities by all of these horseshoe vortexes here, and we sum this with the normal component of the free stream velocity, and it must be 0, because there cannot be velocity in this direction on the wing surface. Now we can calculate this induced velocity if we use Biot-Savaart's law, and as it turns out, this integral here is just a function of the relative position between the vortex and the point. So it's fixed. And what we do now is that we use this for every control point. We build up a system of equations, and here this Cij is just this part here, which doesn't depend on the circulation, and we form this system of equations where the unknowns are the circulation of each vortex. Of course, when you solve it, for each panel, you can use this Kuto-Joukowski formula. With this, now that you know the circulation, to get the normal force on each panel. And of course, you can also get the induced resistance in each panel. And from that, you can sum it up and get total lift and total drag on this wing. You can see that this is much more flexible because you can have quite a wide variation of wing shape as long as you can discretize it in panels. Okay, so that's about finishes with potential flow methods. So now I'm going to pass on to the computational fluid dynamics, because like I said, it's been widely used now to design wings and airplane ships and all sorts of devices. Of course, the difference is now that we are looking to solve the governing equations of fluid motion, including viscosity. And I'm going to show you here it's mass conservation and momentum conservation, and of course you can add conservation of energies, scalar quantities, reactions, whatever you can model, and you can put it there. Of course, this is a very wide field, and I don't have the time to make an exhaustive description, but I would like to say something about turbulence modeling, because when you think about design, at least in the preliminary stages, you have to design to what for. And if, for instance, if you think about an airplane that is making trips, I don't know, from Madrid to China or Japan, well, perhaps not Japan now, but making these large trips, if you think about it, it will fly most of the time at a constant speed and level, except for landing and takeoff. So actually, what we want to find is a characteristic design condition for this airplane. And since it's going to be flying most of the time at 11,000 meters and 900 kilometers per hour, this would be your design condition. So it's a static condition. So that when we talk about turbulence has this very unstationary character. You have to think about if it's worth to model turbulence or not. I mean, if this turbulence, what effect it will have on this mean stationary condition that we know that we're designing our airplane to. So actually, when you think about this, you can go either ways. Of course, you can try to model some of all of turbulence modes. I mean, you can try to model all the spectrum of turbulence, where you go into direct numerical simulation or this large eddy simulation. Here, we'll just model the lowest frequencies, the largest eddies of turbulence, but it's still very heavy computationally. Or you will try to model the average effect of turbulence in the mean flow, in this 900 kilometers per hour flow. In that case, you would use this method called the Reynolds Averaging Navier-Stokes equation. Of course, it's much cheaper, at least in the first stages of design, to model the average effect of turbulence on the mean flow, than to go directly into modeling all of the turbulence and then extracting the mean information. That's what you need. Of course, turbulence later on you have to deal with it when you're doing this more detailed design. But on the first stages, it actually pays off much better just to model the average effect of fluctuations. So in order to use this process called the Reynolds Averaging, where you split the variables into a mean component and to a fluctuating component, which should represent turbulent fluctuations. But this fluctuating component have a zero mean. Now, you have to, when you replace this on the original Navier-Stokes equations, you have to make a lot of math, but then you get, for the mass conservation and for the momentum conservation equations, you get these expressions. And if you note, all the fluctuating terms have disappeared except for this one here, which is the average of the product of the velocity fluctuation. Now, this term is called the Reynolds stress, and it represents the mean effect of turbulence on this mean flow, because this is an equation for the mean flow, but we have here this effect of turbulence here. That's good, because that's what we want to model. Of course, since we're not modeling these fluctuations directly, we have to, since we're not solving this for these fluctuations directly, we have to find a model for the model. So, it turns out that in these approaches, what you usually do is use, I think it's called a Boussinesq approximation, and we model it as a kind of a viscosity term here. Of course, now this turbulence appears here. So this is the mean flow quantities, and now this turbulence appears here, this turbulent eddy viscosity. And that is actually what you have to model in order to get this term. So, if you do dimensional analysis, or before that, if you think about the turbulent motions, their motions, so you can use a velocity and a length scale to characterize them. If you do dimensional analysis, you get some kind of an expression for this turbulent viscosity. You have the density, here you have the length scale, and here it's a velocity scale, which actually this K is just the turbulent kinetic energy, so that you can change it up to a velocity scale. Of course, now you have two more terms that you don't know, and then you have to solve for them. Actually, what this does is that then you introduce two additional equations, one for the turbulent kinetic energy, and now for the length scale, you can use the dissipation rate of the turbulent kinetic energy, because it relates the two, so that you can find the length scale. And actually, when you use these two equations, turbulent kinetic energy and dissipation rate, you'll get what is known as the K-epsilon turbulence model, where the turbulent eddy viscosity is given by this one. So actually, you're using an equation for this one and an equation for this one, so that you can have this one. And you put it there, and then you make some operations on the Navier-Stokes equations. Sorry. Here, and then you can solve for the mean flow. Okay, that's about the turbulence model. Now, I'd just like to show you some details. This is what I did in my master's thesis. I did these experiments in a wind tunnel with this wing, just a picture of the wind tunnel, so the flow is going that way. Here's the wing, so we had to vary the angle of attack to get those lift coefficients. Now, I also model it in using Computational Fluid Dynamics. First thing you note that here you have a rectangular domain, but here you have a circular domain. Of course, this is a question of how easy it is to make a simulation, because if you had to vary each time you want a new angle of attack, if you rotated the wing here, you have to build a new mesh. So that would be very expensive. So instead, use this circular domain, and then you just rotate the velocity vector so that you can get the same angle of attack. So about the meshes, of course, meshing is something that can take weeks or months to do, and it's very complicated. But I just want to show you that the main thing about making a mesh is that you have to put more elements where the gradients are larger. In this case, of course, we expected the gradients of the solutions to be larger near the wing and behind it, because we still have wing effects going up more or less here. So here you can see that the mesh density is much higher here. And of course, over the wing itself, here at the tips where you have flow coming in from below to top, here is where you're going to find the big gradients. So you have to put more mesh elements there. And of course, going to the third level of mesh density, you still have to work with a boundary layer, which is a very thin region where there is large gradients of velocity. So you have to put even more smaller elements here to model the boundary layer correctly. They say that this wing has had 60 centimeters span, And I can tell you that this the first element here had, like, it was 2 microns of height. So it was very, very small elements just to get these large gradients near the wall. Now, to move on to boundary conditions, it's also a very difficult thing, because you have to, since this is a physical model, you have to put the right values as boundary conditions. Now, of course, since we are trying to simulate the results from the wind tunnel test, we use the same velocity here, so that we can get the same, more or less the same flow. But of course, since we're using turbulence, you also have to put boundary conditions on this turbulence on the turbulent kinetic energy, for instance. So it's usually what you do is that you define the turbulence intensity. Now you can relate this turbulence intensity. It's just so this is the turbulent fluctuations. So this is just the root mean square of the turbulence fluctuations over the mean velocity. It just tells you how strong turbulence fluctuations are in relation to the mean velocity. Note that you can relate this to the turbulent kinetic energy, and it gives you a boundary value for the K. And you can do the same with other formulas for instance, the dissipation.
Sorry, what is the relationship between turbulence intensity and Reynolds number? Is there any relationship?
I really can't say between the Reynolds number.
Yeah. Because for me, the intensity of turbulence was something like Reynolds number. But you introduced me something new for me. What's the meaning of that?
Okay. So this is just when you have a turbulent flow, you have velocity fluctuations. Correct? This is just, let's say, an average value of these velocity fluctuations over the mean velocity of the fluid.
So it's related to fluctuation of velocity.
Yeah. It's like if you have, for instance, a 1% turbulence intensity, it means that the velocity fluctuations, jumps in velocity, would be about 1% of the mean velocity of the flow. Of course, there should be a relation with the Reynolds number, but I'm not really clear about how it should be. So, but here now, just for the outlet, just a little note, because on the outlet you really don't know how much, what is the speed of the flow, but actually if you put it far enough from the wing, you can at least say that the static pressure, you can make this approximation and say that the static pressure relative to, let's say, for instance here it was the atmospheric pressure, is 0. So this way you can get a boundary value for the pressure. Of course, all of this is related, pressure and velocity, to the Bernoulli equation, so you can really have boundary conditions for every value. Of course, at the wing, the physical boundary condition is that there is no slipping, because the velocity, the fluid particles on real objects, they adhere to them, they don't slip over them. So you just make it as a no-slip wall, which means that in this case the wing is stationary, so the velocity would be 0 on them. And there is supposed to be here a top boundary, and here at the bottom boundary I use a free slip wall, which is just the contrary of the no-slip. It just means that the flow, it slips through the wall. It's just it's just to make things easier. So because the top is very far away from the wing, so you wouldn't expect the wing to make any effect on the flow here at the top. And on the bottom, you can always simulate it as a mirrored image by using this free slip wall. I'll show you that. Okay, just to finish, almost finishing, actually for the turbulence model, what we use this model is called the Shear Stress Transport K omega model, We didn't use that K epsilon model because it doesn't really give good results when we're talking about aerodynamic flow of the wings. This one is much better, so we use this one. You see that, of course, in those in that kind of formulation that I show you, you just had to replace this epsilon parameter with this doublet parameter, which is kind of the inverse of epsilon, but it actually gives better results. Now, to start off the calculations, the simplest thing is to use an uniform flow with just the inlet velocity all over the domain. Now, there is just a note here, the advection scheme. The advection scheme simply means how the solution is advancing throughout the domain among the simulation nodes. So from some years ago, they started to use this high resolution scheme. I can show you more or less how it works. Let's say here that you have a downstream node, and here is an upstream node, and you can relate the values of this variable u between the upstream node and the downstream node. We're just taking the value of u and just making a first order approach with the gradient and the distance from, let's say, simplify the distance from this point. Obviously, and then you add up this small parameter here, beta. And now, if you put beta equal to 0, you just have the value at the downstream node is just equal to the upstream node. That's called it's called an upwind scheme, because here you're just taking the value up behind, it's coming from the upwind, coming from behind. Now, this is a very stable approach, because very stable approach means that the values of the solution, they don't explode, let's say, but it also introduces a lot of artificial diffusion, so that in areas when you have big gradients of the solution, those gradients, they will be smeared off, they will become more flat, and that can give a lot of mistakes. So when you think you could use this, if you use this beta equal to 1, you get a second order approach. But this also has problems because it doesn't smear the gradients, but it introduces a lot of instability in the calculations, and you can have things can explode sometimes. So what you do with this high resolution approach is that you model this value of beta locally in function of the gradients of the solution. Of course, when you use software, these manufacturers, they don't tell you how they do this. It's their secret. It's kind of secrets of the trade. Now, just to end it, just to find a couple solver. This means a couple solver just means that the equations, they are solved all at once. Mass, momentum, energy, they are solved all at once. Because you can have other kinds of solvers, like segregated solvers. They just solve momentum, and then they solve turbulence equations, and they solve energy equations. It's like a cycle. Now, coupled solvers, they have very nice characteristics. They converge much faster. So we use it because of this. And obviously, just to end it, you have to know when to stop. And normally, these criteria is just these residual things that actually what they are is that. If you remember the Navier-Stokes equation, they are equations that they express balance. So if you could solve them analytically, this balance would be translated into 0 because things are balanced. Now, what these residuals they do is that they measure the difference between the state of balance, where the residual would be 0, and the actual state that you got. Because when you are solving the equations numerically, you are introducing errors of discretization, and so that this balance is never reached. So what you expect is that when you get convergence of the solution, that these residuals they will be becoming more and more, they will become smaller, and then, but of course, you have to say when you want to stop. Here I stop it, and when this was 10 to the minus 5, it's not very stringent, but it's a good criteria for this case. Okay, now for finally for the results that were not very nice. Okay, this is a kind of embarrassing, but see, these are the wind tunnel results, and these are the wind tunnel results, and these are the numerical results. Here you have the wind tunnel results and the numericals. This is the lift coefficient, by the way. This is the drag coefficient. Well, of course, we had a problem with the wind tunnel. And it was that the wind tunnel was close to a window in the laboratory, so we couldn't use it at full power because the window would be blown away. So we had to do. It's true. So we had to do these calculations with the wind tunnel at low velocity. The problem with low velocity, we got very low Reynolds numbers. And what these very low Reynolds numbers they did is that the transition from laminar to turbulent regime is controlled by the Reynolds number. The higher Reynolds number, you have more turbulence. So since we had this low Reynolds number, the flow was mostly laminar throughout the surface of the wind. Of course, when you use this computational fluid dynamics and you use in turbulence models, it means that the method assumes that the flow is turbulent all the way. There was no way to simulating laminar flow and turbulent flow at the same time. So that's why we got this very large difference, especially here in the drag coefficient. Because you can see that the numerical is much lower than the experimental. Because when you have laminar flow over wings, you actually get a higher drag coefficient. That is kind of strange, but it's true. Because normally, for instance, for a flat plate, a laminar flow would give a lower resistance coefficient. But in a wing, I should perhaps in the next seminar I'll explain this. In a wing, in an airfoil, when you have laminar flow along an airfoil, in certain conditions you will get more drag. Okay. And now just, of course, computational, the CFD models, they are useful because you can also get nice pictures. I'm going to show you a picture that shows more or less how was the flow over the wing and several angles of attack. For instance, I'm sorry this is a little small, but you can see that, for instance, at 3 degrees the flow is very smooth over the wing. These are approximately streamlines of the flow. The flow is very smooth over the wings, and you can see, especially here, that the flow is being deflected inwards. This is exactly because you have air from the high pressure side is coming over to the low pressure side, and it is pushing the air that comes from here, is pushing it inwards. If you increase it up to 12 degrees, I can show you that, for instance, this deflection is much higher because this vortex is much stronger now. But also you have this blue area here and here, and this blue area, it represents reverse flow. That meaning that the boundary layer is separated here, and in this area the flow is going upstream instead of downstream. And then if you put it a little bit further, you can see that these zones of separated flow, they are almost touching each other. They have increased a lot from here to here. This means that there is even more separation as you increase the angle of attack. And now finally, here at this angle of attack, you have completely separated flow over the wing. So here the flow is going in this direction, but here on this blue part is going backwards. On the surface, near the surface of the wing, I mean. And actually you can see, like I said before, this was probably the highest lift coefficient, because further than this, the lift coefficient probably start to go down, because you have now a lot of separated boundary layer here. Of course, if you look at this difference, I cannot put my hands on fire that these two pictures are okay. They really express in reality what happened, but still they are useful so that one can understand more or less what is going on. But of course, in the end, and with respect to all the methods, you can see that they have a lot of limitations. So that's why even today, with a lot of computer power and a lot of very highly sophisticated methods, most people will continue to trust wind tunnels. because it's a tried and true solution. And that's it. Okay.
If you go to the previous slide, I understand that the line that you're plotting with the squares is the numerical, so it doesn't have the inconveniences of the that you mentioned of the experiments. But I don't. Yeah, I mean, you say that it's quite faithful. I mean, you know what you're studying, or maybe in the other there are other artifacts. No, my question is that when you're starting to see the boundary layer, I mean, you have a separated boundary layer, I would expect some kind of crossover already. But the line seems quite straight. I mean, only on the crossover is much higher. I mean, you understand my question? I mean, I would expect to have some slightly different slope as you have separated boundary layer, but still seems straight.
Yeah, it's well, I did. This is a very coarse curve because I did very small angles of attack. Yeah, but you shouldn't be. I mean, it's true that when the boundary layer separates, it's true that the flow is going over to a new, different regime, but you actually can still have lift with a separated boundary layer, and it still more or less has this linear relationship. And I can show you. This is about 14 degrees. So, I can show you now the real thing. From here to 14 degrees, you see that it's still more or less.
But this is the.
This is a
from potential theory. Or?
No, this is real flow, wind tunnel results. Of course, it's a different airflow, so we must be careful with that. But actually, you see that even here around 14 degrees would be more or less this. Yeah, you still have this linear. You usually have stall when most of the boundary is separated over all of the surface.
So it's quite linear. So, and the second question, I mean, also regarding the previous plot.
Yeah.
How much? Sorry, this is the computer. How much do you estimate that is the turbulent? I mean, which would be the departure from the potential theory to your turbulent simulation? So,
well,
the lift in particular.
That is actually an easy question to answer because I cannot show because it's graphical, but you see that there is this. Since this line is mostly linear, you can calculate its slope, and from potential theory, you say that the slope of the lift coefficient in terms of the angle of attack is equal to 2 times pi. Mm-hmm. So if we wanted to know the difference, we would draw just a line in radians, with alpha in radians. So we could just draw a line with the slope 2 pi, and we could see the difference between the lift coefficient in potential flow and what you get with this, with using these methods that account for viscosity.
Well, there is some departure because 2 pi would be that coordinates to 1.
That's in degrees. That's in degrees.
It's in degrees.
So it's difficult. Okay. But I can tell because since potential flow you don't have boundary layer separation, you could go up to 1,000 degrees and you still go up to 5 times 1,000 degrees. So if you plot a line here, you could actually see very well this departure from potential flow. Actually, this wind tunnel test, I thought they had problems, but they were very interesting. And I can tell you that, for instance, you see that actually here we have a very good agreement, but from here you see that there is this deflection, and the experimental results, they start to move along this line. And actually this is because of the phenomenon called it's a laminar separation bubble, where you have this but it's a quite interesting phenomenon that happened here. That didn't happen in the computational results because you couldn't model laminar flow. It was just turbulent from the start. Obviously, from the start, when you have this kind of turbulence models, you have laminar flow just over a very small part here in the beginning.
So what is the Reynolds number, more or less, here?
In this simulation,
Order of magnitude?
it's about, I think it was about 19,000.
90, so 9 to the
9 to the 5th.
times to the 4.
92 to the 4, yeah. So it's very low. I mean, this. I can tell this actually the airfoil of this wing, it was designed to work at its most efficiency at the Reynolds number of 1 million. So we were very, very low on the Reynolds number. Of course, at 1 million we would have turbulent flow to be okay.
More questions?
Yes, my question is about the length scale. You mentioned you had to input 2 micron separation between grip points.
Yeah.
Is this also for this simulation?
Yes.
And these scales, this model is describing reality. For instance, if you think of the wing, maybe the surface is not smooth on the micron scale, or
Yeah.
I mean, at this such a small scale, micron scale, wouldn't you expect some corrugation or some?
Yeah, that's a good point. Actually, usually these models they are made to be extremely smooth, to have a very small roughness. Right? That's what I think you were saying. So I don't know what was the roughness here, but yeah, perhaps 2 microns would be. This wing wouldn't be that smooth. But of course, here you have this representation of the surface, so you can make it as smooth as you want. And I can show you, for instance, just that you mentioned it.
This is almost like microscopic scale for matter, no? Micro.
Yeah. You can see here, for instance, that this curve, this is the same airfoil, except that this is for a smooth airfoil, and this is for a rough, with standard roughness. So you can see that the effect of roughness is to increase the resistance, almost double. So yeah, it's probably that this
this scale might be relevant.
It's probable that this 2 microns is too much for this reference. But then again, what usually you have this rule that you say that you have to have at least 15 points inside the boundary layer. But it's just that you don't know how thick is the boundary layer, so you have to make estimates. So these estimates they are based on flow on a smooth plate, so that you usually get this kind of very low values for the first one.
More questions?
Well, yeah, I had a couple. And in your work, when you did for your master thesis, were you analyzing a special design for the airfoil or just an exercise? So were you computing these coefficients because that was a special airfoil design from?
No. Actually, in my department there was some people that were very active on making this radio controlled sailboats, and they wanted to see if this sail would be a good sail for their sailboats.
That's for a sail.
Yeah.
Not for a wing.
Yeah, but actually this is a wing, but they wanted to use it as a sail, so they talked to me and I said, yeah, it sounds interesting to test it. So actually this was for the sail. That's why we have it here. It's a little bit up from the wind tunnel floor, so that you can model approximately the airflow behind the sail, between the sail and the sea surface. Usually, if this was a wing, we would just put it the bottom of the wing close to on the top of the floor.
You have working in a couple of companies in this design of real blades and propellers. What are the methods you were using there, if this can be disclosed? I mean, you use a full direct numerical simulation or large scale simulation, or this kind of modeling turbulence? What did you do there?
It was this kind of modeling of computational fluid dynamics with these turbulence models.
Modeling turbulence with some closure.
Yeah. It was on propellers, but actually you can now when you start designing a propeller, you actually almost every wing that you have to start from scratch, you'll start with this lifting line theory, because it's very simple, and you can find necessary spans, aspect ratios, you can use it, and then when you start developing, getting into more detail, then you start using, for instance, this method, and then you probably end up with this. Actually, I was using this method.
Questions? If not, thank you, João.
Okay, thank you. No sabía.